Right. Let's get started since we have a packed day of talks and program. My name is Venkat Guruswamy. I'm a senior scientist and also interim acting director here at the Simons Institute. And it's my pleasure to invite you all to the Meet the Fellows event. It's also live streamed like all our events. So thanks to those who are watching online as well. So briefly, as you all know, Simons Institute is the leading venue for collaborative research in theory of computing related fields. And it also is one of the biggest convening point for postdocs and fellows anywhere related to theoretical computer science. And we are really proud of our fellows program. So the fellows are sort of in two categories. So we run typically 2 programs each semester, 2 thematic semester programs, and each of them has a cohort of 7 to 8 fellows who are picked by the organizers from a very highly competitive applicant pool. So our fellows are amazing and go on to do great things at the institute and beyond in their careers. And in addition, we also have some continuing postdocs as part of the quantum and machine learning pods. And one of the ways we sort of mark the fellows program is at the beginning of each semester, we have this event, the Meet the Fellows event, which is basically a sequence of talks by the program fellows and some continuing fellows, short talks introducing themselves and their work. And really the idea is to everyone to get to know each other and hopefully find some common points of interest, right? Collaborations, discussions, in addition to, of course, like, telling others about your, things you're most excited about currently. And so it's my pleasure to invite you to that event today, which is co-organized by Nikhil Srivastava, who is a senior scientist also at the Institute, and myself. And so we're going to have 4 sessions of talks. So this is the first session, and I'm going to pass it on to Nikhil to introduce the chair of the first session.
So thanks, Venkat. Welcome, everybody. So the first session, the topic is graph algorithms. We'll have 5 talks about graph algorithms. The first 3 are about very classical problems like minimum cut, shortest paths, and vertex connectivity. And then we'll have 2 talks about kind of more recent vintage problems like privacy and sparsification, which will make a connection to the more kind of linear algebraic aspects of the fast algorithms in data structures and optimization program. So again, the format is we have 15 minutes allocated for each talk. So that's 12 minutes for the talk and 3 minutes for discussion. But really, we would like to keep this as informal as possible. So please do ask questions in the middle, even though it's kind of a short talk. And again, as I mentioned in the email, one of the things to really emphasize is open problems. And so please do try to explain whatever open problems you're excited about. So we'll start with Jason Lee, who'll talk about recent trends in minimum cut algorithms.
Clicker. Introduction. In this talk, I'll be covering recent trends in minimum cut algorithms. I'm from the Simons. So in this talk, we'll be looking at various forms of minimum cut problem. Given a graph, find a minimum size set of edges whose removal distance the graph in some way depending on the problem statement. For example, for global min cut, we just want to disconnect the graph, disconnect any 2 vertices from each other. In the ST min cut, we're given as input 2 vertices S and T. You want to disconnect those 2 vertices. And for the Steiner min cut problem, we're given a set of terminals, T, and we want to disconnect any 2 vertices from T. So in particular, the Steiner min cut generalizes both the ST min cut, when T is just the 2 elements at S and T, and the global min cut, where T is all the vertices. We can also look at harder variants of min-cut where we're required to output multiple ST min-cuts. For example, the single source min-cut, where we're given a source for text, we want to output the ST min-cut for all other vertices T. And finally, the all pairs min-cut problem, where we want to output ST min-cut for all pairs S and T. In this talk, we'll be mainly focusing on how these problems relate to one another. For example, how the time complexities relate to one another. One of the classic results in minimum cuts is the Maxwell min-cut theorem, which says that the ST min-cut can be solved by a single ST max-low call and some linear time post-processing. So here we think of ST min-cut as being solved in max-low time. And by a recent breakthrough in max-low, this can be solved in almost linear time. One trivial observation is that global, Steiner, and single source min-cut can all be solved using n-1 calls to ST min-cut. For example, for global min-cut, we can just fix any source vertex S and iterate over all possible T. And for one of the vertices T, that vertex will be on the other side of global min-cut. And therefore, for that pair S and T, the ST min-cut will be the global min-cut. One classic result in this area is that the all pairs min-cut problem can also be solved using n-1 calls to ST min-cut. Note that this is non-trivial because the trivial algorithm will require n squared min-cuts, and this is a linear number of min-cuts. Another classic result in this area is that it's a Karger's randomized algorithm, which shows that global min-cut can be solved in near linear time without any Maxwell calls. But this algorithm is randomized. So far, we can see, from these statements, we can see a hierarchy of problem complexities. At the top, we have the all pairs single source and Steiner min-cuts, which require n-1 calls to Maxwell. In the middle level, we have the ST min-cut, which requires single Maxwell call. And finally, the global min-cut, which think of it as easier than Maxwell. It requires near linear time without any Maxwells, but this algorithm is randomized. So for a more pictorial view, we see that we can have this diagram where a problem on the left is at least as hard as the next problem in this list. And you can see that there's a big gap between the left and the right. In the left, we have these problems can all be solved in n-1 Maxwells. In the right, we have these problems can be solved in almost linear time. The main question in this area is, are these complexity tight? In particular, this huge gap between at least mn time and almost linear time, or can it be improved? So in the recent few years, there's been some exciting action in this area. The first result in this area is that the Steiner min-cut can be solved in polylog calls to ST min-cut. So colloquially, you can think of this as Steiner min-cut is closer to ST min-cut than single source min-cut. This brings the Steiner min-cut from the left to the right. And this result was sold as the fastest deterministic global min-cut at the time. The second result in this area is that all pairs min-cut can be solved in polylog calls to single source. So note that all pairs is at least as hard as single source, but this shows that these two problems are equivalent up to polylog factors. Another way to see it is if you want to get a fast algorithm for all pairs min-cut, it suffices to only study the single source. And finally, the third result in this area is that the global min-cut can be solved in almost linear time without Maxwell, and the algorithm is deterministic. So here's a new landscape of the problems, where Steiner has been moved from the left to the right, and in fact, it's equivalent to ST min-cut. All pairs and single sources are now equivalent. And finally, global min-cut is also deterministic. But of course, the main open question was still this gap, which is like a difference between mn time and near linear, almost linear time. And this is the gap that we closed. Next, we showed that single source min-cut. So we actually did study single source min-cut instead of all pairs. Can be solved in polylog calls to ST min-cut. The first iteration of this algorithm of this result had additional n squared factor for weighted graphs, which for a technical reason. But this additional runtime has been improved almost linear in this upcoming talks. So turns out this is the final landscape of the problems. They're all equivalent up to like almost any factors. And also global min cut is easier than all of these. They require no max flows, and they're both randomized and deterministic.
What is it? Plus n to the 1 plus sigma 1?
Right. So this means it's an initial overhead, which means that like suppose ideally like if max flow could be solved in near linear time, this will still have an almost linear time overhead.
Just to check, so these are all for weighted graphs also now?
Right. Yep.
Thanks.
So what perhaps is more exciting about these results is the techniques that are used to obtain the results. And it turns out all of these results center around two key ideas. The first is a new parameter called minimum isolating cuts. This is a method to find unbalanced cuts in a graph. And we'll see what unbalanced means later on. And also this idea of expander decomposition, which is decompose the graph into expanders, which are easier to solve, including for min cut problems. So for the rest of the talk, I'll focus on the first idea, minimum isolating cuts, since it's a new idea. So this is the problem statement for minimum isolating cuts is we're given a graph and a set of terminals, vertices. And you want to find for each terminal the minimum cut that isolates that terminal. In other words, the minimum cut separating that terminal from all other terminals. So for example, for this graph, the minimum isolating cuts can be these cuts here. Note that these cuts are disjoint in the sense that the smaller side of the cuts, the cut side that contains these terminals are all vertex disjoint. This is not a coincidence. Turns out we actually crucially use this. The naive solution to this is just simply call one single ST min cut call for every terminal. This requires the size of R many calls. But the classic result that motivates minimum isolating cuts is that this problem can be solved much faster and be solved in just log of the size of our calls. And we call this the isolating cuts lemma. And informally, this means that minimum isolating cuts is essentially a problem solvable in ST max flow time up to this log factor. So this algorithm itself is quite simple. It's like 2 pages of algorithm analysis. But if I had 5 more minutes, I would have actually covered the entire algorithm. But I think what's more enlightening is how it's used to solve, let's say, the Steiner min cut problem. So let's consider Steiner min cut problem again. We want to disconnect some 2 vertices from a given terminal set. And the idea is a very simple random sampling procedure. Let's sample all the terminals with probably, let's say, 1/2, 1/4, 1/8 geometrically decreasing set of numbers. And for each sampling probability, we want to sample every terminal independent with rate P into this terminal set, into a new terminal set R. And we will just call minimum isolating cuts on R. So that's the entire algorithm. And we'll output the smallest isolating cut found over all iterations. And the claim is with high probability, this smallest isolating cut will be the Steiner min cut. So how does it work? Let's consider optimal Steiner min cut, which the algorithm, of course, does not know, but we'll assume for analysis. And let's say S is the smaller side of the Steiner min cut. And now the key observation is that if P is roughly 1 over, this should be the number of terminals in S, then the probability of, this should be S intersect T here. The probability of sampling exactly 1 vertex in this terminal set, in S intersect T, is a constant because in expectation, if for that probability, we'll expect a constant number. And this is like a sum of Bernoulli, so with constant probability, we'll select exactly 1. And if this occurs, then the Steiner min cut found is an isolating cut because we sample exactly 1 terminal, and isolating cuts, that's exactly the problem solvable using isolating cuts. So note that this simple algorithm was the first non-trivial algorithm for Steiner min cut, previously required n max flows. So this really suggests that minimum isolating cuts was like a new idea that really pushed the boundaries for these problems. So that's essentially concludes the technical section of my talk. The future directions, the main direction I'm interested in is directed graphs. In particular, there has been some recent progress on global min cut for directed graphs. So this could now be solved using root n Maxwell calls, but it's still open whether polylog Maxwell calls suffice. Turns out, if you want to consider Steiner min cut problem, we actually realized surprisingly that this problem is actually hard. There is no subquadratic time algorithm for Steiner min cut in directed graphs, assuming popular conditional hardness. And this also since minimum isolating cuts results in the standard min cut problem, this also means that minimum isolating cuts for direct graphs is also hard, and this is indeed true. The same reduction holds. One other direction to take for directed graphs is, what if we compute some sort of directed expander decomposition? Now, this exists, but in much weaker form, and it's an open problem. Can we strengthen the direct expander decomposition to make it work for, let's say, min-cut type problems? And finally, I'm also interested in directed graphs for other problems. For example, parallel shortest path. There's this concept of shortcuts or hopsets of graph, and problems like cycle detection, incremental cycle detection. And for all these problems, I think the main issue that we run into when considering these problems is that we don't understand graph primitives for directed graphs. So we don't understand the direct expanding decomposition. There's a variant of it, but it's much weaker. We don't understand minimizing cuts because it's not possible. Is there another primitive we could possibly use for directed graphs? And if you're excited, if you have any ideas, feel free to talk to me. And thanks for listening.
Jason, any questions? Comments? Yes?
Yeah. I was on, thanks for the talk. I was wondering if at the technical level there's any connection between these stories about global min cut, ST min cut, etc., and the things about reliability, where like the edges are probabilistic and you want to know the probability of disconnecting part of the graph.
Good question. So myself with Demalia and Roshu, who are if not in this audience, also part of this program, have some recent work on network unreliability. So this is unreliability is the problem that Carter also studied. So this is different from reliability because the question is, can we approximate the value? And it's quite different for unreliability and reliability. But for unreliability, we've used isolating cuts to get faster algorithms, and we also used some other ideas I have not covered to think faster. So this is one recent direction that has been studied.
Okay. Any other questions? Hi.
Thanks. Oh, you mean Mike?
Oh, yeah.
Jason.
Or Jason can
So for all pairs max flow, you might expect that it needs n squared because you just have to write down the output. Why can you get below that?
Right, good question. I should have mentioned this in the talk. So we can actually compute what's called a Garmy-Hu tree. There's a single tree whose min-cut values equal the min-cut values of the graph. So more precisely, there's a single tree for which, for any two vertices S and T, the min-cut value, let's say the real number equal to the min-cut, is equal to the same min-cut value in the original graph. So this kind of encodes all the ST pairs. And it turns out like the min-cut itself, if you look at the vertex partition, it also equals the vertex partition for the graph. So we cannot output all n squared values for the ST min-cut, but we can output an encoding, which is like a single tree called the Garmy-Hu tree that encodes all the pairs.
For the Steiner min-cut in directed graphs, is the current best the square root and max flow?
Oh no, so this is actually no subquadratic time. So the best is MN, and I believe that is also the hardest. So the best is just trivially calling M-1 max flow. And there's a conditional hardness saying that this is the best you can do.
So is the conditional hardness n squared or is it mn?
So I don't actually remember.
Okay.
It might have been for sparse graph, so it's n squared for sparse graph
Okay.
with n edges. I don't really remember. It's actually not published anywhere, which is unfortunate. But if you're interested, I can find the paper that it's basically like direct. One of the hardest results I think for like this some problem of like finding like the biggest max flow or something like that. Actually, for directed graphs, turns out that lower bound construction also applies for Steiner.
Okay, well, thanks a lot, Jason. It seems like there's a lot of excitement about this. So yeah, let's move on to the next talk by Nicole Wine, who will